This video is an introductory lesson to atomic structure. You do not need to copy down these first two slides. I just want to give you a little bit of background information. So Dalton was one of the first to come up with a theory about atomic structure. And he believed that all matter was made up of tiny particles called atoms, which we do know now to be true. Atoms of the same element are identical in size, mass, and properties, and we are going to find that that is not entirely true. Atoms cannot be subdivided, created, or destroyed. And atoms of different elements combine to form chemical compounds. How much of this is true? Well, some of the theory has been altered based on new information, but he did have most of it down. This gives us the modern atomic theory. The modern atomic theory says that all matter is made up of atoms. So Dalton was correct about that. Atoms of the same element are chemically similar. So we know now that there are some differences between them, such as a situation where we have isotopes. So atoms of the same element may not have the same mass. And atoms are not subdivided, created, or destroyed in chemical reactions. However, they can be subdivided, created, or destroyed in nuclear reactions. Okay, so first of all, you will want to begin taking notes here. Atomic number represents the number of protons. And it also can represent the number of electrons if we have a neutral atom. Mass number represents the number of protons plus neutrons. So we're going to discuss what components make up the mass of an atom in just a few minutes here. So if the number of protons plus the number of neutrons equals the mass, that means that we can rearrange that equation and calculate the number of neutrons by taking the mass number and subtracting the atomic number. So if protons plus neutrons equals mass, then mass minus protons equals neutrons. Back up here. Okay. So isotopes and ions, these are two definitions that you need to be familiar with. So isotopes are atoms of the same element with different masses. The protons will stay the same, but the neutrons differ. Because remember that in the last slide we said that protons determine what the atom is. So if you change the number of protons, they're not going to be the same element. All right, so one way that we write isotopes is by writing the name dash the mass number. Or we can write it as a nuclear symbol where we write the mass on the top and the atomic number on the bottom. And if there were a charge, we would have the charge up here. And this, of course, is the atomic symbol. So you may have seen examples like carbon for isotopes. So when we are trying to find how old, say, a fossil is, we use carbon dating, because we know the amount of carbon-14 that should be present. And based on that, we are able to determine the age because we know how long it takes for carbon-14 to decay. So these are examples of isotopes. They're both carbon, but they have different masses. Ions have an unequal number of protons and electrons. So they will have an overall positive or negative charge. So for example, they may look like this. And we do typically write the number and then the sign. That's the convention, but if you were to do it the opposite way, I would not mark you down. Chlorine 1 minus or aluminum 3 plus. So here's a breakdown of the subatomic particles that we're going to be discussing. So protons are located in the nucleus. They have a +1 charge, And we have created this unit called atomic mass units. So a proton is approximately 1 AMU. Technically, and you do not need to include this in your notes, but a proton would be 1.007316 AMU. Okay, so we just round that to 1. A neutron is also found in the nucleus, and it is neutral. That's why it's called a neutron. So the charge is 0. And we have also assigned the unit 1 AMU to that because it actually would be 1.008. Okay, so see how they're approximately the same. We round it to 1 AMU. Electrons are found outside of the nucleus, and they have a negative charge, and the relative mass of an electron is 0. So it's not that an electron has no mass, it's just that it's so small that it doesn't really contribute to the mass of the atom. So if we were to write the mass in AMU, it's 0.000549. That's very, very small. Okay, so if you were to add up the masses of the electrons, they're not really going to make a difference. So the example I use is if I were to step on a scale and someone handed me a paper clip, am I going to see the scale move? No, because relative to me, the mass of the paper clip is so small that it really doesn't contribute to it. Okay, so relative to protons and neutrons, the electrons have no mass. Okay, so on your periodic table that I distributed, you're going to see the atomic number up at the top, and not every periodic table is this way, and the atomic mass on the bottom. Every periodic table has a key that shows you where you're going to find each component, so there's absolutely no excuse to not know which number is the atomic number and which one is the atomic mass. The atomic mass is, write this down, the weighted average of all of the isotopes. Okay, so it's not saying that the mass of aluminum is 26.98154. It's the weighted average of all the isotopes. So you would go ahead and assume that probably the most common isotope of aluminum would have a mass of 27. Okay, so we're going to round this number to the nearest whole number. So if the number after the decimal is 5 or greater, you're going to round up. If it is less than 5, then you will round down. All right, so we're going to go ahead and calculate the number of protons, neutrons, and electrons in this element. So protons, you should never hesitate on this. The protons will always be found by looking at the atomic number, which is 13. And previously we said that the mass of a neutron is 1, the mass of a proton is 1, okay, and electrons do not contribute to the mass. Okay. So the mass is made up of protons and neutrons. Oops. So in order to find the number of neutrons, we are going to take the atomic mass, which was 27, and subtract the number of protons, which will give us 14. Okay, and then the electrons, since we don't see anything about this being charged, would be equal to the protons. Okay, and then you can always check your work. So the number of neutrons that you get, which in this case we said 14, if you add up the neutrons plus the protons, you should get the mass. So if we do 14 plus 13, okay, and add those together, we get 27, which means that we got the correct answer. Okay, let me just summarize that here. So protons would be 13, neutrons would be 14, and electrons would be 13. Okay, here's another example. Okay, so the number of protons would be 19 because that's the atomic number. The neutrons would be 20. And I got that because I rounded this number, the mass, to the nearest whole number, which is 39. And I subtracted the number of protons. And if we wanted to go back and double check our work, we know that protons and neutrons make up the mass. So if we add up 19 and 20, our protons and neutrons, that should add up to our mass. Okay, remember that electrons do not contribute to the mass. They're so small that they don't really make any difference, just like handing me paper clips while I'm standing on a bathroom scale. And there's nothing about a charge on this element. It does not say that it is an ion, so the electrons would be equal to the protons. Okay, so I will tell you over and over and over again throughout the year, chemists are lazy, so we try to make things as simple as possible. So when we are using nuclear symbols, you're going to see that because we put the mass on the top and the atomic number on the bottom, it actually makes it quite easy to calculate the number of neutrons, because we know that neutrons would be the mass minus the atomic number. This structure also makes it easier to solve nuclear equations like alpha and beta decay, which we probably will not be getting to this year, but you should be covering in physics if you choose to take that class. Okay, so we're going to calculate these. Okay, the protons, of course, is the atomic number. And notice that it's unlike your periodic table. Now we have the atomic number written on the bottom, but you should know that the atomic number would always be the smaller number because it represents protons, and protons plus neutrons equal the mass. Okay, so the number of protons could not be larger than the mass. That would not make any sense. Okay, so it's set up nicely for you, so we can double check our work too. That 13 plus 14 equals 27, which was the mass number given. Okay, and there is no charge up here. It would be shown up right there. So that means that the electrons and protons are equal. Okay, again, protons would be the atomic number, which was 26. Okay, remember we write it on the bottom for a nuclear symbol and the mass on the top. In order to calculate the number of neutrons, because protons and neutrons make up the mass, we're going to subtract. And 57 minus 26 would be 31. Okay, and you can double check your work. This number, protons plus the neutrons, should equal the mass. All right, and again, there is no charge on this element, so the protons and the electrons would be equal. Now, I do want you to take notice, if you take a look at your periodic table and you locate iron, it's in the middle block. Okay, remember these are in order of atomic number, so atomic number 26. You will notice that the mass that's given on the periodic table, the atomic mass, which was, remember, the weighted average of all the isotopes, this is the mass. So if you were rounding that to the nearest whole number, you would get a mass of 56. So this element, this iron atom, is a different isotope of iron. So it's not the most common one. This is iron 57. Okay, so the mass is not always going to match the mass on the periodic table. The mass on the periodic table is the average atomic mass. Okay, what I give you in these problems is the mass number, which is the number that you will use to calculate the number of neutrons. Okay, now let's try it where we have some ions. Okay, so we've already solved protons and neutrons for this one, so we know this is 13 and 14. But now we have an overall charge on our element. Okay, it is 3+. So what this is telling us is we have 3 more protons than electrons. So each proton contributes one positive charge, each electron contributes one negative charge. Okay, so if we had 13 protons, 13 positive charges, and we had 13 negative charges, overall the charge would be 0. But in this scenario, we have an overall charge of 3. So that means we have 3 more of these than these. Okay, so if I have 3 more protons than electrons, I would get an answer of 10. Okay, so see, I have 13 protons, 10 electrons. That would be 3 more protons than electrons. Okay, so if it's positive, you're going to subtract that number to get the number of electrons. All right, do another example. So we have 17 protons because that's the atomic number. And then we're going to subtract the mass, 35 minus 17, to get the number of neutrons. And you'll get 31. And for the electrons, in this scenario, I have a -1 charge, which means I have 1 more electron than proton. Okay, so if I had 17 protons and 17 electrons, that would add up to 0. But in this scenario, I have a -1 charge, which means I have 1 more electron than proton. So since it's -1, I'm going to add 1 to the protons to get the number of electrons. Okay, but you do need to understand that if it's positive, that means it has more protons than electrons. And if it's negative, it has more electrons than protons. Okay, and then the trick is if it's negative, start with if it's positive, you will subtract to get electrons. And if it's negative, you will add to get the electrons, right? And then it should make sense in the end. Negative means it'll have more electrons. If it's positive, it'll have more protons. All right, so one more example. We're going to compare these 3. Now notice this nuclear symbol looks a little bit different than it did on the last slide. And that is because I left off the atomic number, which would be written down at the bottom. And the reason why I did that is because when I create any worksheets or tests, I am unable to show this number down here. Okay, and it doesn't need to be included because we can find that number easily. Since we are looking at atomic symbol I, which is iodine, I can just go to the periodic table and figure out what number would go down at the bottom, and that would be the atomic number 53. Okay, so that will not always be given to you, but you will be given at least the symbol so you can find out. All right, so let's calculate protons, neutrons, and electrons for each of these and compare them. Okay, so they're all iodine, but there's going to be some differences between them. So all of these are the same element, so they will all have the same number of protons. Let's actually switch colors here. All right, in order to find the neutrons, you've been given a mass number. So since you've been given the mass number, you're going to use that mass, not the periodic table, but the mass number given, because I'm talking about this specific isotope of iodine, this specific mass. I'm going to use that mass to calculate the number of neutrons. Okay, so remember protons and neutrons make up the mass. So I'm going to do mass minus protons to get the number of neutrons. And that would give us 74. 4 for this one. Okay, this one has the same mass, so that would also be 74. Now we have a different isotope of iodine. This is iodine 129. So I'm going to use that to calculate the number of neutrons. That would be 76. And then we'll switch colors one more time for the electrons. So in this case, there is no charge on iodine. So that means that we must have equal protons and electrons. So 53 positive charges and 53 negative charges equals 0. In this scenario, the next one, we have a -1 charge. So we don't always write the 1 in there. It's just like in algebra. You don't have to write 1x. If it just says negative or just says positive, it's implied that there's a 1 there. So I have a -1 charge. So that means I have one more electron than I have protons. So if I add 1 to 53, I will get 54. And here, again, there's no charge, so the protons and the electrons would be equal. So if we call this one number 1, 2, and 3, you can say that 1 and 2 are the same. Sorry, let's say have the same. So 3 is a different isotope. So we have iodine 127 and iodine 129. Okay, so they're atoms of the same element with different masses. So we have a situation with isotopes. And then number 2 has an overall charge, meaning the protons and the electrons are not equal. So it is an ion.